All right, we'll give it about 30 seconds, then we'll get started. All right, I'm gonna go ahead and start. And if anybody else wants to come in, they can just come in and find a seat, and we'll just go ahead and go from here. First question is, how many people in the room use object-oriented programming or use objects in their LabVIEW code? Go ahead and raise your hand if you use them. Okay, of those who don't use objects, how many of you would like to use objects? Oh, look at that. Look at that. How many of all of you feel like you are proficient at object-oriented design? Raise your hand. Okay, maybe 10%. How many feel like you're okay at using objects in LabVIEW, but could maybe use a little bit of a bump in what you're doing, how you're using them, if you want? The rest of you are just here because you got nowhere else to be? That's okay. My name is Dave Snyder. I'm currently working at Coherent down in Portland. We do lasers. That's enough of that. So, what is my presentation about? On the title side, it said LabVIEW, pretty good practices. I'm not going to claim these are best practices because there's lots of ways to skin the cat. These are practices that I use that I found that have been pretty helpful to me. The things that we're going to talk about, some of them are applicable to LabVIEW and LabVIEW or LVOOP. Some of them are more general and just apply to object-oriented programming in general. I'll tell you what this is not about. This is not me trying to tell you that you should use object-oriented programming. I assume you're here because you want to learn about it. If you don't want to, that's fine with me. There are situations where object-oriented programming isn't the best solution. And if you're in that situation, or for whatever reason, business reasons or technical reasons, that's okay with me. This is also not a presentation where we're going to sit around and debate the relative strengths of object-oriented programming versus procedural programming. If you want to do that, we can do that, just not right now. What it is I'm going to try and give you some tips and ideas to introduce you to some tips and ideas of things that will help you improve your object-oriented designs. Okay, tip 0. Learn to read text languages. How many people in here are comfortable reading text languages? Raise your hand. Excellent. Why is that important? Because there are lots and lots of resources available on object-oriented programming. How many resources are there available for object-oriented programming in LabVIEW? 1? Not much. So you're going to get the most benefit from reading these other resources, finding them, reading them, and learning how to translate them into the LabVIEW paradigm. Okay, tip number 1. If you're making a shift from structured procedural programming, which is more or less traditional LabVIEW programming, into object-oriented programming, the very first thing you need to understand is thinking in objects is different than thinking procedurally. It requires a different way in thinking about the composition. About decomposition, about how you break down your problem, about how you think about it, about how you approach the solution. To give a little bit more of an example, or a little more concrete, first thing you need to do if you're going to start thinking about objects, when you're given a problem, what do most of us do as engineers? Okay, I've got to do A, B, and C in order, so let's start thinking about that. And in our head, we think about this flow chart, all the things we have to do, and maybe we'll go here and maybe we'll go there. Don't do that. You need to step back from the process, step back from the details. You need to think more abstractly about your problem. For instance, think about the problem that you're facing. Suppose we're making a river monitoring device. What are the things that are in our river monitoring device? We have some instruments, probably a flow meter that measures how much water is going by, maybe a depth meter that measures how deep the river is, and we can estimate the volume of water that's going down the river at this time. So these are things, these are kinds of noun type things that exist within the problem domain that we've been asked to build a solution for. These nounish type things are good candidates for becoming classes in your application. You also think about the verb-ish kinds of things that these nounish things do. Okay, we've got a depth meter. What does it do? Well, it measures depth. We've got a flow meter. What does it do? Well, it measures the velocity of some fluid that's going past it. These verbish things are good candidates for methods of those classes. Now, I assume that most people here were at the intro to object-oriented programming. People are familiar with the terminology, objects, classes, and methods. Okay. Additionally, as you're thinking about your objects, your nounish things, think about the kinds of information they are responsible for. A depth meter is responsible for knowing what the depth of the river is. It's not also responsible for knowing what the humidity is or counting the number of water bugs that are there. It's responsible for what it is responsible for. So think about responsibilities as you're thinking about your problem domain. Understand the difference between an object and a class. I missed the intro presentation, so I don't know if they covered this. The class is what we do in source code. When we have a project open, we have a class. That's what we see in the project file. An object is what exists in the runtime engine when the program is running. This can be a source of confusion. I know it was a source of confusion for me when I first started learning object-oriented programming in LabVIEW. But it is an important distinction to be aware of, especially if you're reading the literature, if you're going online and reading stuff about it, understanding the difference between the class and the object. Also, understand the difference between the interface and the implementation. The interface, just abstractly, I'm not thinking of Java type interfaces or C# interfaces, but just abstractly, the interface is the collection of methods that you're using to execute some sort of process. The implementation is the stuff that's underneath that you don't see when using the interface. So make sure you understand all that stuff. Or better yet, learn about it if you don't understand it. Tip number 2, you gotta be sure to manage your dependencies. I mention this in almost every presentation I ever do, because it's something that I see frequently not done. There's something called the law of Demeter. That law, which like all software laws isn't a hard and fast thing, but it says talk only to your friends, not to strangers. What does that mean? Well, let's go back to our river application, our river monitor application. And I've just thrown something up here. We'll just assume that it's a well thought out architecture. We've got our UI application coordinator that coordinates the information from these 3 different components, and an instrument coordinator that collects information and talks to the instruments that are actually in the river. Okay, so talking only to your friends, not strangers. We want our UI to display information from the depth gauge, right? So we need some of that. We need to enable that somehow. In my project, in this particular project, I've got 4 classes. I've only implemented the UI application coordinator, instrument coordinator, and the depth gauge. The other ones I've left off. But here, in my user interface, I've got a read depth method. That's what the user interface is going to use in order to get information from the depth meter. Then in my classes below, I've got some accessor methods. My application coordinator has an accessor method that can return the instrument coordinator object. That has a method that can return the depth gauge object. And then in my depth gauge, I have a method that says read depth. So within my user interface read depth VI, you can see here's my accessor. I'm pulling out an object, another accessor. This brings out my depth gauge, and I can read the depth. Okay, that's one way to solve that problem. If you're familiar with text languages, it's roughly equivalent to this kind of dot notation, where we are returning objects and returning objects and returning objects until we get to the object that has the information that we want. Now, is that way of implementing this talking only to friends? It's not. If you're going to be talking only to friends, here I've modified this project a little bit. You can see here I've added 2 more VIs in these middle layers. Here I've got, and they're both said read depth. I added those 2 VIs. So instead of returning the object, I've implemented a method that reads the depth. And within the lowest, my instrument coordinator one here, I've implemented that. We're returning the depth gauge and reading the depth directly from that. The next level up, in this read depth VI, I'm returning the instrument coordinator object and calling the method that I just showed previously. And then my top level does the same thing. So, which, I forgot about this, in text languages is much simpler call. We're not digging all the way through. So back at the beginning, when I said our UI needs to have that information, the first example was reaching through all these layers to get the depth gauge object and then getting that information. Instead, what we're doing is we made multiple steps through. We're getting the same information, but we made it, some will say, more complicated. So the question is, why is this way, quote unquote, better than this way? Any suggestions? Or do you think it's better? Do you guys think it's worse? Yes?
One thing that comes to mind is that you left off all the error handling and stuff, but with multiple calls, you're going to have to handle all of those potential errors. If any of those modules have problems, communications issues, where it's going directly, it seems like you can only have one error wire to handle.
Okay.
Don't know if that's really true, because under the hood, if it's just calling sub-accessors and more sub-accessors, then it still has to handle it. It's doing it behind the scenes.
Okay. So you said the error handling is essentially more complicated, or it could be more complicated using this method than with this method. That's true. That's totally valid. John?
The top one is better because you've abstracted away how you're getting this information at what levels. Each level abstracts it further down.
Okay. John claims that this way is better because it hides all the implementation details that go on down here. It abstracts it all away. Any other thoughts? Yes, in the back.
What happens if you change which flow meter you're using?
That's a good question. And that's an important question. What happens? I'll actually talk about that a little bit more later on. So, I prefer this way. If somebody's going to do it this way, I'm not going to tell them they're wrong, but as with all things in programming, there's trade-offs. I prefer this way, largely for the same reasons that John said. For one thing, if you do it this way, you're embedding in the code the structure of your program. if you ever change the structure of your program, you're going to have to modify this code in order to reflect the new structure that you have. If you make a change to the lowest level depth gauge, then that change propagates up through all the layers. Whereas, in this kind of a topology, if we make a change here, we can limit the effect that that change has on the rest of the application. So we're protecting our application from change by doing that, even though it seems to be more complicated in the beginning. Okay, so manage your dependencies, don't reach through layers.
Seems like it'd be easier to reuse.
I'm sorry?
Reuse would be easier to what you suggest, because it's at a lower level, or rather than be at 3 levels if you want.
Yeah, you certainly you could. The first way, it actually wouldn't. Let me go back here. In this way, you can certainly grab any level and the stuff below it, and just grab that and take it out and move it somewhere else if you wanted to. The first way doesn't prevent that either. It doesn't stop you from pulling that stuff out because the top level, the UI, is dependent on the other stuff. The lower stuff isn't dependent on the higher stuff. If some of this lower stuff was dependent on stuff in the UI, then you'd have a very difficult time pulling that out and reusing it. And I'm not going to talk about this, but just as a note for the rest of you, for reading on your own time, if you haven't heard of the dependency inversion principle, that's worthwhile reading, and dependency injection, which is very, very useful if you are trying to test your classes. Dependency inversion principle will help in decoupling. But again, like all things, there's a trade-off there. You're adding more abstraction, which adds more complexity in exchange for getting that decoupling. Okay, tip 3, encapsulate what changes. Okay, back to our river monitor. Here, we could have written read depth or read depth VI in the user interface this way, where this is not real code, it's just to illustrate the idea. Or we're making a visa call directly to the instrument. We could have done that. But, as was mentioned, what happens if we suddenly have an installation of the software that uses a different depth gauge? A depth gauge from ACE instead of our cool Acme depth gauge. The way these are often handled is by casing it out. And you check to determine whether or not what type of depth gauge you have, and then making the appropriate call based on your depth gauge. That's something that we've all seen. What are some of the downfalls of that approach? Pardon?
Every time you add something, you gotta change.
Every time you add a new depth gauge, you have to change the code, which risks introducing new bugs. And you're gonna have to go through and regression test everything in order to make sure your application still works. Another problem is that what if you end up using 30 different depth gauges? Now, but each site only uses one. You've got a lot of extra code in there in order so that the application works across all your installation sites. That exact problem happened to us at the last place I worked. We had an application that was written quickly, and it was being deployed on RT platforms. And it got so big and so bloated that it would no longer fit on the RT platform. So we had to break it out and use more of a plug-in architecture for that. So looking at this, now we have 2 depth gauges that we want to use. This is our good Acme depth gauge. We want to add an ACE depth gauge. So what we do is we take our existing code, we move it down, we add a depth gauge interface. This is a class, I'm going to call it an abstract class, meaning there's no implementation behind it. There's nothing in the block diagrams, it's just connector panes. It's a class that is not meant to be instantiated at runtime. We are never supposed to have an object of this type going on. But we want the front panel, my brain just skipped a beat. We want the front panel, and we want connector panes, so we can use them to invoke methods on our depth gauge classes, our depth gauge objects. So then we implement the Acme depth gauge, and we implement the ACE depth gauge. And this way, in this way, what changed was the depth gauge, and the encapsulation allowed us to make that change relatively painlessly. It limits the kinds of changes that we have to make to our application. So a question that's often comes up is, all right, we have to encapsulate what changes. How are we going to know what changes are going to be requested? The answer is, you don't. You just kind of, knowing your problem domain, knowing your customer, you have to make educated guesses. Sometimes you'll be right, sometimes you'll be wrong. I don't know of any good way to figure that out. If you guys have ideas, let me know. Also, as with all things in programming, you can overdo it, you can take it too far. You can over-design your application. Be aware of that. I think it's not uncommon to do that. I know I did it plenty of times when I was first learning. Instead of over-designing, what I tried to do is develop a development process such that it's easy to adapt my application to the changes that come in, even if I can't predict what changes they will be. Okay, tip 4, use creator methods. All right, most languages, and since everybody in here knows text languages also, you know that text languages have constructors. For instance, Fido equals new dog, right? We also know LabVIEW does not support constructors. You can't write a constructor in Lab. So the question is, here we have a depth gauge object at runtime. It's going into a depth gauge method that is supposed to return a number. Is that valid code? Yeah, that's valid code. But the real question is, will this code work as expected? Anyone? Who think, okay, no, I'll be a little more direct. Who thinks this code will work as expected? Awesome. Who thinks it won't? One. What other answers are there? Nobody knows if it will work as expected. You guys are too smart. It might work as expected depending on how it's implemented. For instance, let's say in my read depth measurement, I wanted to take the average of the last 5 measurements in order to reduce noise. And the way that that has been implemented is that I'm maintaining an internal queue in this object of length 5, and every time I get a new reading, I do a Lossian queue, so it'll push the new one on and pump the oldest one off. Then when I do a read, I'm going to flush the queue, calculate the mean, and return that number. So, is this implementation going to work as expected? Nope. No, and we can see why. So, we've identified the need, or I pointed out a situation where a constructor might be helpful, but the question why doesn't LabVIEW support constructors? It's actually an idea that has been requested many times of NI. Does anybody know? Yeah.
Isn't your constructor technically when you drop the class constant on the block diagram?
More or less, yeah. So in the text language, a constructor is code that you can write that will run whenever the object is instantiated, right? In LabVIEW, there is no object instantiation at runtime. It happens as soon as you drop the constant, the class constant, on the block diagram. You're essentially instantiating that object. And there is no opportunity for us to write custom code when that object cube gets dropped on the block diagram. All right, I've had discussions with R&D about this, and one of the problems is that we also use the object cube on front panels, in which case that creates a lot of problems. And when you add it all together, it's just not feasible for LabVIEW to support constructors. So we can't have them. The solution instead is to use a creator method. Instead of using object constants or class constants when you need to instantiate an object, I always create a VI, and I call it, in this case I would call it create depth gauge. And anytime I want to instantiate an object, I drop this instead of this. Inside the creator, in this particular instance, I'm doing this, I'm initializing my queue, obtaining my queue, storing it in my class data, and that's it. And then that way, there's another method here that I did not implement or show, and that's essentially, take a reading and put it in the queue. We'll assume that that's done offline. But even if I didn't have that internal queue, I would still have this creator. Even if I have objects that are purely by value, have no reason that they have to have a creator called, I will do that. And I do that precisely because I don't know how that class is going to change in the future. In the future, I might want to put a reference type inside the class. And if I don't use a creator, if I use this method instead, then I have to go through and I have to create, for instance, either a creator or an init method, and I have to go back and add that everywhere that class is used. Chances are good that I'm not going to remember everywhere that it's used. By using the creator method, I've given myself a space where I can do any future modifications that might be necessary in order to get that class to work. Are there questions on that? Yeah?
Do you know of a way that, I like this, do you know of a way to lock down the class constants so that you don't have a row developer drop that?
I do not know the way. Do you?
No, I didn't think there was, but.
Yeah, I don't think there is either. I mean, if you put it in a library and you make it private, you do, but it's not a very good solution because lots of times people need the access to the class constant so they can put it on front panels for terminals for inputs and outputs. So there is not a good way to prevent them from dropping the block diagram. So it's just part of my methodology now, is that the only time I ever use a class constant is if I'm doing upcast or downcast.
That sounds like a great VI analyzer test, which is find it afterwards.
What word?
A great VI analyzer test to find it afterwards.
You're right, it does.
I can teach you how to write those. Next year.
All right, I'll look for it. Okay, so tip number 4, use creator methods, even if there is nothing to initialize in that particular class. Use the creator method, write a creator method, use it, make it part of your pattern. It'll make things easier in the long run. On your creator method, be sure to have required input terminals for any data the object requires in order to function. That way, you can be sure that when that object comes out of the output terminal, That is a fully initialized and ready to go object. You don't have to remember, oh, I have to put init on it before it will work properly, or anything like that. You want the object to come out ready to go. Within your creator method, be sure to initialize any private data values that are required and create any reference types that you need, be they queues, notifiers, refnums, whatever needs your object needs in order to execute. You want to be sure to do that in your creator method. Destructors are a good idea too. Most of my classes will have a destroy VI, and essentially that's just a spot where I can clean up the references that I've initialized in the creator. And just as using those has become part of my pattern also, even if there's nothing in it. So one last thing about this I wanted to point out, this is kind of an advanced idea, is this is the front panel for my creator VI. If we look up here in my terminal, you can see my depth gauge input terminal is right there instead of normally where it is right there. What doesn't show is that terminal, I also set it as optional. It's not required, it's not even recommended, it's optional. The whole reason I have that there is it makes it easier to test in that I can create child classes of this. For instance, this represents hardware, a piece of hardware. I can create a child class from this and implement a software mock. And then in my test code, I can put my software mock on the input terminal there, and the object on the wire as it goes through will be my mock software, as opposed to the real hardware. It's a way that allows me to test the software even if I don't have the hardware available. However, software mocks and testing, that's a whole other full day topic, so we'll stop there. Tip 5, favor composition over inheritance. When I was learning object-oriented programming, and I'm sure many of you have encountered this too, inheritance is always heavily emphasized. Heavily emphasized. It led me to believe that inheritance is the reason you want to use object-oriented programming. Talking to other developers, they've expressed a lot of the same thing. However, inheritance is not a silver bullet. It's not the solution to all problems. It is another tool, another capability that helps you solve problems. It is also invariably overused by people new to object-oriented programming. Again, because it is emphasized so heavily. That's my belief. For example, let's assume that let's pretend we're making a game. And this game has a dog, right? So we create a dog object, and the dog barks. And because cats rule the world, we create a cat object too, and cat meows. And of course, a little bit later on in the development of this game, we decide they both need to eat, so we implement some eat methods. But because we're good designers, we pull those combine methods up into a parent class we call animal, and each can inherit the eat method. So we're reducing our duplicate code. And on the other side, we have a robot that cleans up the eat, because dogs and cats are messy eaters, and because we get tired of cleaning up, we also have a robot that kills them when we're tired of them. And of course, all robots need to be able to drive, so we implement a drive method and then smartly pull it up into a parent class so that we can do that. Okay, so we've got this very simplified model of an application we've written, and we've released it, and it's out in the wild for months, and it's working well. And then somebody, the manager over the project, comes back and says, well, I want something else. I would like to have a robot dog that can kill things. And this dog has to kill, and has to drive, and has to bark, but it can't eat. So the question is, how do we fit that into our object hierarchy in order to implement that? The answer is, you don't. You can't, especially in LabVIEW that does not have interfaces or multiple inheritance. It's just not going to work. You could actually implement something where the dog killbot has a eat method that you override and have it throw an error. That's a possibility, but it's not very. It's not a robust coding style. It's not a good practice to do that. It's better just to not make that method available at all if it doesn't apply to the object. So, back to, remember we're talking about favoring composition over inheritance. If we use that example with composition, we've got our four main objects there. Okay, the one thing I do is, all right, I'm going to create another object that I'm going to call eater. It's not related to inheritance, it's just a separate object. It implements eat. I'm going to do the same with drive. The dog and the cat will delegate the eat responsibility to this, meaning they will call this eat method within this eat VI. Same with the driver. And then we can do the same thing with our dog killbot, with the drive and the bark and the kill. We can delegate that responsibility to different objects. So what does that look like in LabVIEW? All right, here I've got my my killer class and my kill method. You can see, all right, well, I've got some inputs and some outputs. That does what it does. In my killbot, which delegates to it, you can see right here, I just gotta keep walking around with my arm out.
Yeah.
Right here, so this is the cluster of my my killbot. Thanks. This is the private data in my killbot. You can see that I've got a killer object in my killbot. So when my killbot kill method is called, I'm going to retrieve my killer object, and I'm going to call the killer's kill method. So that's delegation. The killbot, the application code is calling the killbot kill method. The killbot is delegating that functionality to the killer object in that way. And it's the same thing in the dog killbot as well. So, favor composition over inheritance. This is an interesting quote I came across that kind of summarizes exactly why inheritance is so hard to do well. It says, inheritance encourages you to build this taxonomy of objects very early on in your project. This is before you know all the requirements of your project, maybe. When you build these taxonomies of objects, they become rigid. They're hard to change, and they're hard to adapt to new requirements and new changes. Okay. We got here about 10 minutes. All right. So I just told you to, more or less, don't use inheritance. But that's not very realistic because there's times when inheritance is required, either because you have a quick fix that you need to get out and redesigning your architecture just isn't viable in the 2 days you have. So you've got to patch things, incur some code debt. You got to figure it out. And there's also valid times to use inheritance. So when you do inherit, has anyone ever heard of this? That is a relationship. You've heard? We've got a few. Okay, well the idea is if you can relate two objects with an is-a clause, they're a good candidate for inheritance. For instance, a dog is an animal. Therefore, a dog can inherit from an animal. Okay? That's the idea. And you'll see that in a lot of literature. You'll see it on the web. A lot of people promote that. Forget it. It doesn't, my experience is that it does not work as well as people think it does. Yes, it does. Because the way that we relate things as being is something does not work well in the way that inheritance works. Let me show you an example. I have an ellipse object, right? My ellipse object has a couple methods. I can set my radius 1, I can set my radius 2, and I can calculate the area. Well, a circle is an ellipse, right? So circle should be a good candidate for inheriting from ellipse. So in my circle object now, I've got set R1, set R2, and calculate area. Is that a problem? I've never seen a circle that has two different radiuses. So what would the expected behavior be of this circle object? If somebody writes code that essentially set radius 1 to 10, set radius 2 to 5, and calculate the area, what's the answer going to be? You don't really know. That's valid code, but if there's a circle object, if that operation is done on a circle object, it's not very clear exactly what we're supposed to be getting. Incidentally, this is a well-known problem. You can look it up. It's called the circle ellipse problem. That circle ellipse problem is an illustration of a violation of what's known as the Listov substitution principle. The Listov substitution principle applies to inheritance and helps instruct you on when inheritance is a good idea and when it is not. And the fundamental idea behind it is any child class you create should be able to replace a parent class on your block diagram, and everything will still work. Another way of thinking about it is a child class method cannot have stronger preconditions, and a child class method cannot have weaker postconditions. So let me just talk about preconditions and postconditions for a second. Let's say I have a method that takes the absolute value of a number. So a postcondition of that method, it's kind of an implied postcondition, is that the output value is going to be 0 or greater. It's never going to be a negative number. If I were to create a child class and override that method, and that child class method had a weaker postcondition, meaning a bigger space of possible outputs, negative numbers, for instance, the code that calls that is going to be getting outputs that it does not expect, and it could lead to errors. Alternatively, the stronger preconditions. When we have inputs on a VI, there's some space of valid inputs. We could calculate them all, we could count them up, but there's going to be some number of valid inputs. If we reduce the number of valid inputs to that VI, that's creating a stronger precondition. And we can't do that, again, because the calling code may use that entire space, or may use inputs that are outside of our new reduced scope. Is that clear? Okay. Tip number 6. Again, when you inherit, okay, forget the is relationships. Instead, use behaves like. If something behaves like something else, it's a good candidate for inheritance. What does it mean to behave like something? Well, as in the example of the circle and the ellipse, an ellipse has certain behaviors. Those behaviors are defined by the methods that we created in the ellipse class. We could set radius 1, we could set radius 2, and we could calculate the area. Those are the behaviors that define it. A circle does not behave like an ellipse because a circle only has a single radius. it doesn't have a second radius. So therefore, a circle is not a good candidate to inherit from an ellipse. Okay, tip number 7, eliminate object type checks. Let's go back to our river monitor here. We're just going to look at this particular part right here. Instrument coordinator, the depth gauge, interface, and then we've got our 2 depth gauges. Within our instrument coordinator read depth method, in this particular case, I'm unbundling the interface class, depth gauge interface, and I'm calling the depth gauge read method. Depending on which object is on that wire, whether it's the Acme depth gauge or the ACE depth gauge, the appropriate method will be called. The correct method for that object will be called. Now, and that's done automatically via LabVIEW, Magic, and Dynamic Dispatching. Another way to implement the same kind of functionality is this. Okay, we've pulled out this object, this guy right here. We're checking what the name of that class is. So we're going to check the name. If the name is Acme depth gauge, then we're going to downcast it, this wire, into an Acme depth gauge wire, and we're going to call the Acme read. And then, of course, in the other case, we do the same thing with the ACE depth gauge. You can see in this case, the ACE depth gauge also has another method that we have to call before we can read the depth. So, remember, I'm telling you not to do this. Why would you not want to do this? That's kind of a bad question. I'm sorry, I take that back. The reason you don't want to do this is because, generally speaking, your parent class does not have any dependencies on your child class. You can take that parent class somewhere, and you can take it into a different project if you wanted, and you'll be fine leaving those child classes behind. When you do this, your parent class is now dependent on your child classes as well. You have to take them as an entire bundle. If you pull just the parent class out and you take it somewhere else, you're going to get all sorts of errors when you try and open it up in a new project because you did not bring the children classes along as well. Plus, the other reason it's generally poor programming practice is that you're essentially doing the exact same thing that dynamic dispatching is doing, except it's much, much slower to do it that way. All right, we've got just a couple tips left, and I don't have a lot of, these are just kind of quick run through things. So, learn to think like an API designer when you're writing classes. One thing I like to tell people is, whenever you're writing code, you're also writing an API. Whether you think you are or not, whether you intend to reuse it or not, it doesn't matter. You're writing an API that somebody else is going to have to read. Maybe that somebody else is you in 2 years, but you're going to have to read it. So think like an API designer and try to make your API to your class as easy to use as possible. Again, that alone could be a whole other presentation, so here's just a few points. Think about the principle of least astonishment. This principle states that when you show somebody a method or a code or a class and they're reading through it and they're reading the methods, they are going to be least astonished by what those methods actually do based on your class and your methods and your names and whatnot, and your inputs and your outputs. If you have an add method that instead subtracts, there's going to be a lot of astonishment. Bad idea, right? So principle of least astonishment. Strive for orthogonality. What do I mean by that? Well, if you think of a helicopter, did anyone ever flown a helicopter? Hey, got one. So, if you have a helicopter and you're hovering and you move, what happens if you just move one control and leave everything else the same? I mean, sure, it's going to depend, right? But if you move one control, you typically have to compensate for that movement by moving the other controls as well, correct? Right. So that's non-orthogonality. changes in one thing require changes in everything else as well. Think about your APIs or your public methods to your classes. You want each method to do something that doesn't affect other parts of that class. That's what I mean by orthogonality. If you get large classes, when you have large classes, that's typically a good time to look at them and maybe break them up into smaller classes. The single responsibility principle states every class should be responsible for one thing only. Now, that one thing can be a large thing. My rule of thumb is if I can describe what that class does in a single sentence without using and, I'm probably okay. If I have to use and or any other conditionals, maybe I need to take a look at that and think about breaking that up into separate classes. Single level abstraction principle, I'm going to skip over that. Command query. In general, there's a lot of VIs, and this is not targeted at you, Bruce. There's a lot of VIs, and I've seen a lot of people write, and I've even written some myself, where they have setters and getters combined into a single one, right? It's a set get property, and people will often wire a Boolean into that to determine whether or not they're trying to set it or get it. That doesn't help with clarity, because as you're reading code, you see this VI that says set get, and you see a Boolean wired into it, and maybe there's more than one Boolean wired into it, and you don't remember exactly which one it is, and so you're having to search, hover over things and read the context to help and figure out exactly what that VI is doing. In general, it's better to separate your commands from your queries, your getters from your setters. Lastly, classes and libraries, for that matter, provide lots of options for scoping your methods. Scoping can restrict who can use your methods. Use it. Make things private if your users of that class do not need to use that. Make as little of your class public as you can get away with, because it will make it easier for you to maintain it and change it in the future. And my last tip was just file management. This is my preference. I like to maintain a flat file structure with my classes. I'll create a class, a directory with the same name as my class, and I'll put everything in that class in that directory. I don't create any subdirectories. I don't do any hierarchy in that. I do that part in the Project Explorer using virtual folders. It's a lot easier to move things around in the Project Explorer, put them in virtual folders, without having to worry about then changing them on the disk structure in order to maintain that. I do the same thing with libraries. If I have libraries that have several classes in, I'll create a directory for my library. I'll put my LVOOP file in that, and I'll create subdirectories for every class in that library. And the reason I do that is because if you have a class that's in a library, you can't extract that class and use it somewhere else. You have to take the whole library. So it makes sense to keep them all together. And that's just enough. We'll skip that. Lastly, something for you guys to research later, look up on your own and read about. Solid principles. Who's heard of solid programming? Okay. These are some principles that have gained a lot of traction in object-oriented programming. If you haven't heard about them, I encourage you to read up on them. They can be fairly complex, not immediately obvious how they apply or why it is true, but it's well worth your time to investigate it. And that's it. Thank you.